I'll do it.
Okay, great. Okay, again, if you have anything against recording, please let us know.
Okay, thank you. No, I don't mind that
Great.
presentation is recorded.
Okay, so you can start. Thank you.
Okay. Let me have it ready before sharing the screen. It will be more efficient. Here and share the screen. Perfect. Let me also have a quick timer. Just normally we should have some time for questions at the end, but just to be safe, let me put the timer. Okay, perfect. So good morning, everyone, again. I'm presenting here a joint work with different collaborators. So it's a regroupment of different works on the development of an algorithm for solving a certain class of separable non-convex mixed integer nonlinear programs given an arbitrary numerical precision. And the key here is to manage the scalability. That means to be able to solve problems even when either the precision becomes small or the size of the problem is correlated, of course. And this is the result of collaborations with Julien Cotzy and Bernard Gendron from Montreal, Claudio Pontardo from Montreal also, and Julien is currently in England. Okay, so the quick outlook. First, I will motivate the work and present the exact type of case study we are interested in. Then I will present the algorithm we propose before a little focus problem that needs to be tackled efficiently in our work, which is a particular piecewise linearization. And then I will conclude and be ready for questions. Okay, so let's start with the motivation. So we are interested in optimization problems that can be modeled in this form. We want to minimize the function over some linear constraint, and this function is we are considering in this case separable function. It would have been a too long talk. I tried to introduce non-separable functions, but the talk was too long. So that means that can be expressed as, and each term is expressed as a function of a single variable. So obviously, if each function is linear, we get a mixed integer linear program because the variable x can be divided into real variables and integer variables. And if f is a non-linear, we have a mixed integer non-linear problem. We can have some special properties on f, like convexity, etc., but we are not going to consider this case. We are going to consider general nonlinear function f, but we are going to assume that we have the expression, the mathematical expression of the function. So we're not doing black box optimization, for example. This problem has numerous fields of application, and I'm going to present some of them when I present the result in energy optimization, transportation, etc. Okay, in general, we have classically two types of approach. I'm going to go quickly through this phase. The idea is that either you consider a generic mixed integer nonlinear programming solution methods. That means that do not require any specific properties from the problem. In this case, usually you manage to obtain global optimality if the method goes to completion. And usually the downside of the generic mixed integer linear programming method without any particular property is that the size of the instance solved may be small or medium if we do not have any special properties. It's like a linear programming based solution method. Here, the idea is simple. You approximate the nonlinearity with piecewise linear function and you solve the problem. And after solving the problem, you analyze the solution. If you're happy with the solution, then you stop. If you are not, then what you can do is try another approximation. Usually what is done is you fix the number of pieces. For example, I will approximate with 3 pieces, and then I obtain my function. After solving the problem, if I realize that I'm not satisfied with the solution, then I have to repeat the process with, for example, 4 pieces, etc. Now, the downside of this approach, the main advantage first is that the problems are more tractable, because then you can take advantage of the efficiency of mixed integer linear programming solvers. But there are several downsides to this approach. It's a try and error approach. You don't know in advance how many iterations you're going to need. So it's a try and error approach with no guarantee on the quality of the solution. And you don't know in advance how many iterations you are going to need. Also, at the end, even if you are satisfied with the solution you obtain with 4 pieces, for example, you don't know if the solution will have been improved with 5 pieces or with 6 pieces. And even if the solution was not improved with a higher number of pieces, for example, if you are from 5 pieces, you did not improve the quality of the solution, you still do not have the guarantee that moving to 6, 7, or 8 will not have improved the solution. And finally, global optimality is not guaranteed. So for scalability, this both approach as is are not necessarily ideal. The first one because of the size of the instance that basically can be solved usually, and the second one because the more pieces you use, the larger the problem. And in any case, you don't have any guarantees. So let me now make a focus in the state of the art on some methods that have some key components that we are going to be inspired from. The first one is a spatial branch and bound. So, spatial branch and bound. So, classical approach, of course, for global optimization. The idea is to maintain both lower and upper bounds to compute usually a convex relaxation of the problem and use that to obtain the different bounds. And if you do not manage to prove the global optimality, given the bounds that you have computed, then you split the space in 2 subregions and you repeat. Note that in this case, in the case of nonlinear problems, global optimality is assumed attained as soon as the gap between the lower bound and the upper bound is lower than a threshold that has been predefined. It could be 10 to the power of -4 or whatever. So it's usually global optimality given the desired precision of the solver or others. So if you have not proven the global optimality of your solution, then you split the space into 2 and you tighten it. Basically, if we illustrate it here, if we have this nonlinear function, okay, visually we can see that the optimal is here, but of course we do not know that, the solver does not know that. So what it's going to do is a convex relaxation of that, then compute the optimal solution, different bounds based on that convex solution, which will bring us to this point. And then what is going to happen is that the domain is going to be split into 2 subdomains. And on each subdomain, we can tighten the relaxation. And we repeat the process. Now, this is the first approach based on global optimization. The second big approach, as we said, was based on piecewise linear approximations. And usually in this case, the approach will consist in constructing a function that will interpolate the nonlinear function at the breakpoint. In this case, the finer the granularity, the better the approximation. So the more breakpoint you authorize, the better the is going to be. The numerical guarantee in such approach will depend, of course, of the size of the discretization. So the error that you're going to make with this approximation will depend on the number of breakpoints. Very rough guarantees. I don't know what happened, so let me just go back to here. Can you all still see my screen?
Yes.
Let me
But it
pause
looks that there is
here.
some problems for hearing you correctly each time.
I think it's working. Oh, the sound is not good?
Yeah, sometimes we are losing the sound, yeah.
What can I do?
I think nothing. Yeah, it just it just for a few seconds, so that's fine. I think it just 2-3 seconds from times to times, so I think it's fine for the moment.
Okay, so let me try again, but let me know if you cannot hear me. I can switch network.
Okay, let's do like this. Thanks.
Okay. So here the tractability will be attained only for rough guarantees because in order to have a very small discrete, very small precision, you will need a lot of pieces. And for each of these pieces that you introduce, you will need a binary variable that will tell you whether this piece is used in the optimal solution or not. And remember that this is for a unique nonlinear function. And in your mixed integer nonlinear program, you have several nonlinear functions that are summed up. So this multiplies. So usually, recently, some approaches have tried what is called adaptive refinement. So the idea is to try to find the global optimal solution of the MINLP, but by solving a series of mixed integer relaxation, increasing the accuracy only gradually. So let me show you the two recent works that did that. The first one is the work from Bourla et al. And in their case, they consider mixed integer linear programs with a linear objective and nonlinear constraints. Note that in this case, we can transform this problem, to go back to the problem, the class I presented before, because you can always replace, you can always put that our nonlinear objective can be replaced by a variable, and we put a constraint, a linear constraint, that the variable is equal in our objective. So basically, we can always convert our problems into the class of problems that Bourla solves. So this applies. And here, there are two critical components in the way they applied their method. The first one is on how the piecewise linear functions are defined, and then how they are later on refined. And here, the key idea is that we can see illustrative case here, case on the figure. If we look at the figure on the left, the piecewise linear function interpolates the nonlinear function. That means the breakpoints are on the nonlinear function. And the idea is that we can either overestimate or underestimate here. If we use 3 pieces, for example, what we are going to compute every time is the polygon that will contain the nonlinear function, and we are going to compute the piecewise linear function in the polygon. In this terminates after a finite number of steps. I had a weird noise. Is everything fine? Let me see.
From my side, yes. I didn't hear anything.
Okay. Okay, maybe it was a disconnection. Perfect. Thank you. It proves they prove that the algorithm will stop after a finite number of steps, which is an important property to have, convergence property to have. Let's call it NB, B for Bourla, and epsilon will be because this finite number of steps depends, of course, on the precision required. They use mixed integer polyhedron to compute the lower bounds. That means instead of having the function in black, we'll replace it with the domain. So what we are going to say is that in this, from between -1 and 1, the function has to vary in this domain in blue. And then every time we do that with a fixed number of pieces that has been predefined, we need a nonlinear programming solvers or Oracle to compute the maximum linearization error every time we split each into 2. So the piecewise linear function are defined polyhedron. The breakpoints are on the nonlinear function. And to refine the procedure, what they do simply is that they split every time the function if a sector is used, they will simply split it into two, exactly like the special branch and bound did, split into two with less or equal and greater or equal the point. The second approach was by Ngueveu et al. 2019. They used that and implemented a solver that is now available as a package, Julia, that is called Alpine. And the idea here is to split the domain not into two, like Bourlacou did, but in three sections. And the middle section, the idea is that it will not be three equidistant sections, but the middle section will be the smaller one, and the rest will be the rest. And the size of the middle section will depend on a parameter given the user. This parameter is called delta. And I'm not going to detail exactly where it comes from, but just to give you an idea, fixing a value of delta equal 8 means that the middle sector here in yellow should be a fourth of the total domain. So the intuition of Ngueveu et al. Is that we should not use equidistant split when we split it, but we should be tighter that was by the current solution, and then leave the rest approximated less precisely. But to define the size of this yellow portion, you have to decide in advance what will be the size. So if you want the size here to be a fourth of the total domain, then you need to put delta equal 8 simply. Now, their proof of convergence is weaker than Bourlacou because they were only able to prove that it converges one number of breakpoints increases to infinity. They were not able to prove that it can converge in a finite number of steps. And this is available in a solver Alpine. Now the algorithm we proposed is simply the following. With different, let me focus on the specificity of this algorithm. The first one is that we want to have a precision-driven refinement instead of domain-driven. What it means is that instead of pre-deciding that I'm going to split the domain into 2 or 3 or even 4 pieces, we are going to define the precision we want and compute the optimal refinement related to that precision. Okay. So instead of fixing the number of the split and then using a nonlinear solver to compute what is the error due to the number of split that we decided, we are going to do the exact opposite. We're going to redecide the precision we want, and then that means we need to solve to optimality the problem of finding the optimal refinement given the precision that is given. Second key difference with the state of the art, the literature, is that we are not going to interpolate. Our piecewise linear function is not going to interpolate the nonlinear function. What it means is that we allow our breakpoint to deviate from the nonlinear function. But there is no reason to impose the breakpoint to be on the nonlinear function. So here. Also, we are going to allow our piecewise linear function to be not necessarily continuous. That means we do not impose the discontinuity, but we do not impose continuity either. We are just going to compute the best approximation, and we do not care if it is continuous or not. After that, what we can do is that we can solve a single mixed integer program to obtain both the lower and the upper bounds. All you need to do here is compute a piecewise linear function that is actually an underestimator of your function. And by doing that, the mixed integer program is going to give you a lower bound. After doing that, because the nonlinearity is restricted to the objective function, we know that this solution can be feasible, will be feasible in terms of it will validate all of the constraints. So all we need to do is recompute nonlinear function, what would have been the real cost of the solution we just obtained. And in this case, we obtain an upper bound. So we obtain both a lower and an upper bound by solving a single mixed integer linear program. Mixed integer linear program, sorry. And if we are unhappy with the result, of course, we are going to tighten only the necessary pieces. So here the idea is that if at the end I want a precision of 10 to the power of -4, instead of approximating everything with 10 to the power of -4, we will mean I will obtain a lot of pieces and a big mixed integer linear program. I can start with a precision of 10 to the power of -1, for example, solve the resulting problem, and then tighten only the sub-pieces that were used by my solution. In what I aim by that is to avoid the multiplication of the number of pieces in my problem, which means I want to keep my mixed integer linear program as small as possible. And in spite of that, I can still prove that we convert it, but by tightening only the interesting part of the research domain. And so all of those part of the nonlinear functions that will never be used by the solution, they will not be tightened in terms of precision of the piecewise linear function. So there is no need to be precise in that zone. So with this, our goal is to solve small mixed integer linear programs at each iteration. What is interesting with this precision-driven refinement is that we could prove two different things. The first one, we were able to prove the convergence in a finite number of iterations. I'm going to skip the idea of proof here. So that was the first point. So this will converge in a finite number of steps that is relatively small. And the second important precision is that if you remember here, this NB epsilon is the number of iterations that the algorithm of Bourlacou is going to need. Remember that there were two algorithms from the literature, Bourlacou and Nagarajan. Nagarajan could not prove that he has a limit in his number of iterations, but Bourlacou could for his algorithm. And Bourlacou, his number of iteration was this one. And the idea is that we were able to prove that our algorithm will converge in a number of steps that is less than the logarithm number of, which means that even from a theoretical point of view, converge much faster. So that was a nice result to obtain. So the key benefits is we keep the scope of the update locals. So in this case, this is what allows the scalability, because even if the size of the problem itself increases, the number of pieces that we add in our problem is still limited. We refine based on target precision, not based on an arbitrary number of breakpoints, which improve the efficiency of the method and has some nice properties. And the on-premise the search case will listen anyway, so that's good in terms it saves time. And on high dimension, this helps, of course, to solve problems with very small numerical precisions. So I'm going to show some results, for example, with precision around 10 to the power of -4, which was difficult, which was not tractable with another method. So in order to illustrate the efficiency of this, we used different classes of optimization problems. Capacity facility, either nonlinear warehousing cost or nonlinear assignment cost, a transportation problem with nonlinear transportation cost, a multi-commodity network design with nonlinear cost. I'm not going to present in detail each of these problems because I'm going to present an aggregated result anyway. The detailed results are, of course, available in the paper. So in overall, if we aggregate the results, we get here in the exact the number that are solved. And in the y-axis, we have the CPU time in seconds. Note that the y-axis is in a logarithmic scale. And we compare here a different approach and different, these were nonlinear programming solvers with our method. So the blue and the blue dot and the red dot, the first two here, are two variants of our method. One is with an aggressive tightening up principle that I did not detail, and here is with a conservative tightening. So the difference between the two is basically when you are not satisfied with the solution, so you are not satisfied with the precision you chose, which precision you will use at the next step. For example, you start with 10 to the power of -1, and in the aggressive tightening, for example, at the next iteration, the piece that was used will be tightened with a precision of 10 to the -1 divided by 2, and then next iteration divided by 2, etc. So that will be the conservative tightening, sorry, and this will be multiplied by a factor just to see what happens. We see that overall the efficiency of both are quite similar, whether you are aggressive or not. It doesn't make a huge difference in the result. But in any case, these are still order of magnitude smaller than the result of all other methods. Note that here some problems, if your problem was, I'm not saying if the sort was easily the problem, like Baron, in a very small computing time, it is possible that this iterative approach is not necessary. Finally, what I want to highlight here is that the green line that is here is the naive approach. So basically, it's the equivalent of our approach, but with no iterative refinement. So what it means is that you just simply decide to approximate all of the nonlinear function with your target precision. If your precision 10 to the power of you already approximate 10 to the power of -4 and you solve. So here we see that, yes, our approach of iterative approach allows us to gain in terms of time and scalability. But that being said, the naive approach, the baseline method, was already pretty good. So it is also an advantage here. And I'm going to talk about why later on. So also we try to compare. The list here do not have the solver that I presented at during the literature review. It was done by Nagarajan. It was not presented because it was not able to solve the problems due to the size of the problems that were solved, that were handled. For example, for the transportation problems here, we had to generate very small instances in order to be able to compare ourselves here to Alpine. And for these, we could see that the computing time was instances that called by both method. Okay, and very quickly Alpine reached its time limit. Okay, so to summarize, we have here an approach based on an adaptive refinement of the piecewise linearization of a problem. So instead of approximating to the target precision, you need to approximate to a precision that is gradually refined. And with this, you can significantly size of the problems you can with the method. In order for this to work, let me go back quickly here. You need to be able to solve efficiently the precision-driven refinement. That means you need to be able to compute very quickly the optimal number of pieces in the optimal piecewise linear function given a target precision. So I'm going to mention it here. So the precision-driven initialization and the precision-driven refinement, they require to solve a problem that is mean the number of pieces on the bound constraint. So I fix the error I want, and I want to minimize the number of pieces, and I need to be able to do that efficiently to be able for the method to work. Now, why is this problem difficult? This subproblem. This subproblem is difficult because it is a semi-infinite program. Basically, what it means is that you have to make sure that your solution, you have a constraint that says that at any point of the domain, between the approximation and the nonlinear function must not exceed that on any point of the domain. The domain is continuous, so you end up with an infinite number of constraints. And also, in this case, trying to compute iteratively each linear piece is not optimal. Basically, we have an illustrative case here where we have a nonlinear function in black here And due to precision we want, our goal is to say with the black lines, the thinner black line upper. Here we can see that if we decide to maximize at every iteration, if we decide to compute the segments one by one, maximizing at each iteration the length of the segment, well, the solution we'll obtain is not optimal because it will contain 3 pieces. Basically, we'll go from A to C. And that is the longer possible. And then from C to D and D to F, that's the optimal solution would have been to move from and then B to E directly. Okay. There were a few pre-existing studies on this case, focusing mainly on continuous piecewise linear approximation. And if you remember what we said before, we do not need the continuity. So if we look at not necessarily continuous piecewise linear function, which is a recent line of work, what was interesting is that we have a theorem that says that I compute not necessarily continuous function. That means if you do not impose continuity, then now maximizing the domain length of each segment is optimal. That means I can compute each segment separately, and each time I'm just maximizing the length of the interval covered. In addition, by authorizing discontinuity, you can also reach a fewer number of pieces. So here we have an example again. Same figure as before, but the domain goes to 6 from 0, whereas before it was from 0 to 5. Basically, the optimal continuous piecewise linear function has 3 pieces. It goes from A to B in blue, then B to E and E to F. You cannot do better than that. But if you authorize discontinuity, you can go directly from A to C and then start from D to F. So in 2 pieces, you obtain the piecewise linear function. What we did then is that we developed a geometric approach in order to solve this problem efficiently, because this is a problem we are going to solve 7 times for each nonlinear function at each iteration. So we need the CPU time of this to be, for example, much less than a second to compute the optimal solution. In order to do that, we develop a geometric approach based on the notion of corridor. So a corridor is simply a space between 2 nonlinear functions that are continuous, but that never intersect. So here we have 2 illustrations, the figure on the left and the figure on the right. Of corridor, it generalizes many types of metrics. For example, if you want to have an approximation error of less than delta, then between your approximation and your original function, then you can build a corridor which will simply be the function plus delta and on the upper as the upper function, and then the function plus minus delta as the lower function. If you want to have a relative error, that means you want the error to be expressed in, then same thing, you will have the upper function will be 1 plus epsilon times your original function, and the lower one will be 1 minus epsilon times the lower function, times the original function. So this is a generalization of the type of error, which means I do not need to care about where the error comes from. I just need to have my upper function and my lower function. Note that it can also be used either to approximate the function, also to compute on underestimators. You just need to choose your overestimator. This notion of corridor and the geometric approach was very useful because we're able to have strong theorems based on that. In particular, if the corridor is convex, meaning if both functions are convex, both limits of the corridor are convex, then we were able to characterize very precisely what is the optimal first piece of your piecewise linear function, and then you just have to repeat the process and compute the second linear function, etc. And here it was that each linear piece will have its breakpoint on the lower limit of the corridor and will be tangent to the upper limit of the corridor. So with this characterization, we have a very specific characterization of the function, so we know very precisely what we are looking for, so we can be very efficient in its computation. We have actually a logarithmic conversions for computing each segment of the piecewise linear function. In the case the corridor is convex. In the case the corridor is not convex, options. Either you split the corridor that are either convex and concave. Note that if the corridor is concave, for us is the same as if it is convex. You have to multiply by -1. So we also have a very tight characterization of the linear piece we are looking for. So convex case and concave case are easy. So either you divide your corridor into subcorridors that are purely convex or purely concave. In this case, what you obtain is the heuristic of optimality. It is not it's a heuristic with a performance guarantee because the error is tightly bounded. Basically, what we proved is that if you divide your domain into, for example, 3 subcorridors, then we are sure that your heuristic would give you a solution that will have a number of pieces that will not exceed optimal +2. Or if I give another example, if you split your corridor into 2 subcorridors, you know that is either the optimal solution or +1. So there is a bound on the number of extra linear pieces you have. So this is a heuristic, but very tight, with the very tight solutions. Or we have an exact method that is based on an iterative approach based on function sampling that I will not have the time to detail here. But the advantage of this, in any case, is that we are able, using all these properties, to have very efficient algorithms. And these algorithms are already available. So you can run them yourself. You can just use the package. It's just a Julia function to call, and everything works. To illustrate the benefit of that, here in this table of result, I take, for example, this polynomial function, polynomial, and then we use different values of delta when we want to approximate. And we see that when we look at the state of the art before, that was computing continuous piecewise linear functions, the computing times were pretty high compared to what we are able to achieve with our package that we call the exact method work in a few seconds. That again, remember, is a very tight, very good solution with bounded extra number of pieces, is extremely fast as well. And to show the efficiency of it, we simply took a problem of multi-community network design with congestion. No need to detail the problem too much, but the point is by applying this linearization on the nonlinear functions and then solving the problem directly with simplex, we were able to obtain CPU times that are competitive with advanced state. So you can imagine that if instead of using C++, you use decomposition method, etc., you can reduce this computing time even more. So the strengths, the impact of using this arbitrary, of being able to solve the sub-problem of computing the optimal piecewise linear function given a precision and optimal in terms of number of pieces, is that the method which consists in approximating the function that's solving, this can be pretty effective, is what we showed. But the weakness of that is that if your epsilon is very, very small, even though we computed optimal piecewise linear function, you're still going to get a number of pieces that is pretty important. Also, if you go to very small values, you might reach issues of precision on your solver. I'm talking about very small precision, for example, like 10 to the power of -8 or something like that. If your precision is 1%, this is not an issue at all. You do not even need our iterative approach. Just use the straightforward approach with the package linear and it works. We are getting very, very small to have a method that could be called exact if the precision is equal to the internal precision of the solvers. So this will work, but we will usually work for rough guarantees on large problems. And finally, there was a line of work which consisted in decremental or iterative sampling, which was based on the idea of computing an optimal solution to a problem by building an optimal solution to a smaller number of problems and building on it. A bit with like the logic of dynamic programming. You want to solve a problem of size n, but you start with a problem of smaller size. But the principle is a bit different, but let's say it's the same logic. So the idea was, can we solve our problem using a similar approach as this? Because this has been shown to improve the scalability of the problems it was used on. And the idea is yes, basically. If we think about it, which consists in this session with gradually increasing accuracy. So this is actually the iterative method that we had. Yeah. So the iterative method can be seen also as a way to improve the scalability of the baseline method. In conclusion, we've presented an iterative method. We do not say anything about the resulting. In this case, you solve it with a linear programming solver, but of course you should apply also on a line of research is to apply a specific dedicated decomposition method. If your problem is a specific problem, like network design, for which we know that there is efficient decomposition method, or vehicle routing or scheduling problem. But the advantage here is that we have a method that can handle arbitrary numerical precision. Among the key component of the method, it was the fact that we keep the refinement very local, having too many pieces, and it's easy to compute optimal piecewise linear function given a bound on the error that we authorize. The piecewise linearization are computed with a package that is available. And the next step is, of course, having a dedicated method for the second step, a dedicated decomposition method, and working on the non-linearly separable case, which is what we are doing now. And yeah, what we are doing now. Just a quick word on some tools and useful package that could interest you if you are interested in this line of research. The first one I mentioned is Lina, the packagization. The corresponding paper is under review in a journal, which also reviews the code. So we made the code, okay, it was already available here, but one requirement was to put it in a public repository. So it is on a public repository. And what I wanted to mention is on that repository, we plan to put all of the code, also for the non-separable case and everything. We plan to update this repository usually with our different findings. And our next step is to make it on the algorithm, iterative algorithm, any user can plug in directly their own problem, meaning you can plug in directly your own original nonlinear problem, and it will do the decomposition itself, the approximation, and all the iterative process. And all the code will be open source anyway, so you can fine tune and personalize anything you need. Thank you for your attention. I hope
So
it was understandable and it's not got too much.
it was understandable. I'm trying to clap virtually and making the sound.
Thank you. Okay.
So are
So
there
if you have any question?
Yeah, sure, please. Any question from the audience?
Yeah, maybe it was clear enough.
It was clear. I have just if there are no questions from the audience, I have just a curiosity question. Did you try to check if the two questions. First, if the theoretical what is the, let's say, the ratio in terms of iterations of your method with respect to the one proposed by the author starting by B that I forgot the name?
Okay, you're maybe mentioning here. So there were two methods from the state of the art. This one from Borlaku, which had a
exactly.
Okay, a proven proof of conversion in a finite number of steps, and then Nagarajan did not have does not have a proven guarantee of conversions given a number of for a number in a finite number of steps.
Yes. So I was wondering if in practice, okay, you show that your method, there are two methods that converges, yours and the one by Borlaku. They are the only two where you can have a proof of convergence. Yours seem to be faster theoretically, and in practice, what's the ratio? Is it more than the theoretical ratio, or it's exactly the theoretical ratio? I don't know if you see my point in terms of iterations.
That's a good point. In practice, we do not know yet for a simple reason. Is that Borlaku, in all of its his computational experimentations, he used mixed integer nonlinear problems where there were both nonlinearities that were separable, but also nonlinearities that were not separable. And at this stage, we are finalizing, applying the optimal refinement on functions that are not separable. So we will not, I don't need to implement his method to code ourselves his method to compare, which we did not have the time yet to do, or to extend our method in order to handle to be able to handle non-separable case and then be able to compare. So our choice here was to work on extending our work, but then the extension is working on progress. So a direct comparison. So because we had a theoretical comparison, we were not so worried. So we decided not to prioritize spending time re-implementing his method.
Okay, yeah, definitely. It was just, I have a curiosity when I see theoretical, bounds. Yeah. I'm curious to see in practice if it is at least like this or if it can be better. Okay, thanks.
Thank you very much.
Are there any other questions from the audience? So, if there are no additional questions, I'll thanks again the speaker.
Thank you.
And